At this point, we've talked about the truth tables, and I'm hoping that we're all pretty comfortable with using the truth tables to prove the validity or lack thereof in sentential logic. Okay, so what we're going to do is take a look at direct proof in this video. We'll look at some ways of using the rules of inference, etc. But just to review, let's see where we are. So we've seen that there's a mechanical procedure for deciding the value of any truth functional schema, and we saw how that recipe works. So what we're going to say is that if a truth functional schema comes out true under all interpretations of its sentence letters, then we'll call it valid. If it comes out true in one or more of its interpretations, we call it satisfiable. Now, what do we mean when we say that one set of sentences implies another? Or what do we mean when we say that some sentence follows logically from some other set of statements? What do we mean when we say that it's implied by some statements? As we've seen, we can check to see whether entailment holds or whether the conclusion is implied by the premises by using the truth table. And we have a recipe for doing that. So one more time, you should all know this at this point, but just to run through it, we're going to treat the premises as the antecedent of a conditional, and we're going to treat the conclusion as the consequent of a conditional. And then we'll work out the truth table for the conditional statement as a whole and see what we get. So once again, the first statement in a conditional is called the antecedent. The second is called the consequent. In this case, we'll take the premises. We will conjoin them all. We'll join them all with ands, right? So you've got a list of premises, then a conclusion. Take the list of premises, join the premises together with an and, then put your parentheses around that big conjunction, then join the premises to the conclusion using the horseshoe. Now you've built this conditional, and then run the truth table, and if the truth table comes out all true, then you know it's a valid argument. So one more time. So if the conditional statement that you build from the premises is antecedents and the conclusion is consequence always comes out true, then the second statement follows from the first, is implied by the first. Okay, so now we've seen in the previous video on rules of inference what these rules of inference are, and what we're going to do right now is do some examples of direct proof using the rules of inference. So this is going to be an additional technique. Let's see. So that's our recipe for using the truth table. Now, if we had to deal with something more complicated, let's say we had something like the following. Let's say we were given if P then Q or not R. Let's say we had R and P and not S. Therefore Q or M. Okay, let's say we're given something like this, and we're asked to decide whether this conclusion here follows validly from these premises. So we were going to go ahead, we'd apply our recipe. In order to do that, we'd have to string the premises together with ands. So we do something like we do if P then Q or not R and R and P and not S, then Q or M. So notice what I've done here is this section here is the conjunction of the two premises. And notice we only have two premises. Here's the conclusion joined together with the conditional. Then we'd run the truth table on this. We'd run the truth table and determine whether or not this came out valid. Now that's going to be a pain in the ass because first off, look at how many variables we have here. We've got 1, 2, 3, 4, 5 variables. We've got 2 to the 5 lines on the truth table, 2 to the 5 rows on the truth table. And that's too much, too many. So I'm not going to go ahead and we're not going to go ahead and build a truth table for that because that's just horrible. But that's how we would do it, and so we know that there is a recipe for doing that. So let's see, what do we do then? How do we go ahead and prove this in a sort of less cumbersome way? Well, we use rules of inference. So we saw the rules of inference in the previous, in one of the previous videos, the video entitled Rules of Inference. And what are those rules of inference? Well, they're valid patterns or valid ways of inferring some schema from some other set of schemata. And what we can do is treat them as shortcuts for solving these kinds of problems. So we remember, if you go back and look at the video, you've got modus ponens, modus tollens, simplification, De Morgan, etc., etc., etc. And you know that if you're following those rules, then you're not doing anything wrong, and your inferences are valid, and you can go ahead and give it a shot. So how do you do that? Well, okay. So if you remember from geometry, I don't know if you did anything like this. You probably did. You had some basic axioms, and from those axioms you deduced theorems. We're going to do something similar here. So here the axioms, instead of axioms, we've got premises. So here's our first premise. Notice I numbered. That's a number. That's the number 1. Now I've gone and destroyed it, but let's see. Let's clean it up a bit. So we number our lines, and there's a kind of bookkeeping technique here, as you'll see, that you know, different instructors, different logic books will give you different bookkeeping techniques, and depending on how much of a stickler your instructor is, they'll sort of take points off if you don't follow the right method for listing the steps, etc. There's good reasons to care about these things, but I am extremely sloppy, so I just want you to get the proof done. It's good to number. It's good to account for things. It's sort of like accounting, right? So, but you know, I won't be fully consistent. I'll do my best to be consistent, but I'm notoriously bad at staying consistent and doing my bookkeeping. So you've got if P then Q or not R. And we'll go ahead and say that that is a premise. I'll write the thing out so you see. So what I've got here is I've got the number of the line, I've got the schema that I'm talking about, and I've got the reason I did it. So the reason it was introduced. So what makes it okay to introduce that as a premise, or what as a line, and the reason is because it's a premise. So every line has to be justified, and this over here, this everything to the right hand side will be the justification for the introduction of a line. So line 2, I'll introduce my other premise, R and P, and not S, and that I'll say how I got that. That's a premise, and the goal then is to build the conclusion. So there's my conclusion. So the idea is, how do I get to Q or M given these two premises? So I look at the rules of inference, and the rules of inference, as we saw in that previous video, apply to the main logical operators. So what's the main logical operator in these cases? Well, in the case of the first one, this is the main logical operator, first premise. In the case of the second, this is the main logical operator. Okay, so just as a kind of also to give you another recipe, how are we going to go ahead and begin here? Well, we could just think about which of our rules of inference apply to the main logical operators that we have at hand in this case. So on line 3, I might say, well, look, I can apply the rule of simplification to line 2. So let's go ahead and do that. So if I apply the rule of simplification, as we saw in the previous videos, so I can simplify a conjunction. I've got a conjunction here, right, with these two conjuncts, and I can simplify to conclude the other conjunct. And if I want to, I can go ahead and apply it again. That's also from line 2 by simplification. Okay. Turns out there won't be any need for me to do that, but that's all right. Line 5, what have I got here? I've got R and P on line 3. And so I can say R from line 3 by simplification. Line 6, and so you see how that worked. And what I'm doing is I'm accounting for where over here in the justification column, I'm explaining how I got that line, how I got line 5. So I'd say, if I'm reading over here, I'll say, I got line 5, which is R, from line 3 by simplification. Now, let's say I'll just apply a rule here, and I'll explain why in a second. So on line 6, by double negation, I got not R from line 5. Now, why did I do that? Well, I did that because I wanted on line 7, P then Q from lines 6 and 1, disjunctive syllogism. Now, just to explain that, so what I did is I knew I needed P if P then Q, right, on a line by itself. Why? Well, I'm trying to get Q or M. I know that if I get Q by itself, then by the law of addition, I can just go Q or M. Okay? So all I need is the Q. Where am I going to get the Q? I'm going to get the Q right here. How am I going to get that? Well, it's stuck. It's stuck inside this complex sentence. So how do I get it by itself? Well, the rule of disjunctive syllogism would allow that. So disjunctive syllogism, just to remind you, is if P or Q and not Q, then P, right? Something like that. If, in order to do that, then I would need the negation of not R. And the negation of not R is not R, or R. But to apply the rule of disjunctive syllogism, I'm going to say not R, the negation of the second disjunct. That gives me P or Q, if P then Q on line 7. 6 and 1, disjunctive syllogism. Line 8, let's see, what have I got here? If P then Q, and I need P. Where am I going to get P? So for P, back here, handily, I've got R and P. I know that I can get P by simplification from line 3. 3, simplification. Okay, so line 9. This is getting horribly messy, I'm sorry. Line 9, I've got Q. And how did I get Q? I got Q from 8 and 7 modus ponens. And once I've got Q, then on line 10, I have barely enough room on the screen, but Q or M. Q or M from line 9 by the rule of addition. Sorry about my sloppy writing. I'll try and be neater in the next one. So just to talk you through that then, so what did we do? So this is a direct proof of Q or M. This is what I wanted to conclude down here. Remember, this was the original problem. I've got my premise, and conclusion. What we did is we introduced the premise on line 1, first premise, second premise on line 2. Then we looked for the main logical operators. So we tried to figure out, well, what am I going to do here? How am I going to get the operators? Break them apart, or do I need to? So there's one operator. Here's the other MLO for each of these premises. I've got some rules of inference. I know, for example, that disjunctive syllogism applies to a schema who has its main logical operator as a disjunction. I know that simplification applies over here if I've got a schema like this one whose MLO is the AND. So I went ahead and I did that. So on line 3, what I did was I went ahead and I simplified this MLO, and I've got R and P on a line by itself, one of the conjuncts. R and P on a line by itself. I did the same thing, but it didn't really matter for no real reason. From line 2, I simplified also, and I got not S right there. I've got R. How did I get R? I got R by simplification here. And then I ended up needing to simplify again on line 9, remember? Whoops, sorry. Did I? No, line 8, sorry. From 3, also simplified. Okay, this is getting seriously messy. I hope you're not watching this on a phone. You won't be able to see a thing. Let's go with... Okay. So we've got R and P on line 3 by simplification. We've got on line 4 not S by simplification. On line 5 we've got R again by simplification from line 3. Now we've got not R, and this is where some strategy came in. So I used some strategy. What's my strategy? Well, I'm trying to get to Q, trying to deduce Q or M. I know that I'm not going to find M anywhere in here, but if I can find Q, by the rule of addition, I can get to Q or M. So all I need is Q. Where's Q? Well, Q is right here. It says if P then Q or not R. So if P then Q or not R over here. So if I can show that not R is not the case, then P then Q must be the case. If P then Q must be the case, and I've got P, then I can conclude Q, then I've got Q or M by the rule of addition. So, okay, so now it's basically illegible, I'm sorry. So if let's backtrack. So from line 10, I got line 10 from line 9 by the rule of addition. What was line 9? It was P. How did I get it? I got it because I had what? I had by, you can always check. Oh man. Okay, it's too messy to probably for you to sorry about that. Let's go ahead and try cleaning this up a bit. How am I going to do that? That is funny. I'm not going to erase that video just because it's an example of how things can go. But let's go ahead and I mean, if you couldn't make head or tail of that at the end, I'm sorry, but you can go back and rewatch it. Sort of like being in a real classroom. All right, so line 1. I'm going to give you another, let's do another proof. I'll try and be neater and tidier here. Let's say you've got P or Q or R. And let's say you've got not R and not Q. And let's say you've also got if P then S. And let's say the conclusion is S, just to make it easier. So here's a simpler one. I'm again making this up on the fly. You've got 3 premises and a conclusion. let's start, before we start doing the proof, let's do some analysis. Let's see what we've got here. So here's S. S is the conclusion. You're trying to get S out of all this stuff. So where is S? Well, S appears here, but it's trapped inside a conditional. If P then S. So if P then S is what we have. So in order to get S out of this, unless it appears somewhere else, which it doesn't, we'd need P. So if you've got P, then you know S follows. Well, do we have P elsewhere on a line by itself? Well, we don't. So where does P figure? It shows up here. Okay, so we know that if we had P on a line by itself and we had if P then S, then we could conclude S. Okay? All right, we've got P here, but it's trapped inside a disjunction, which is also trapped inside another disjunction. So what this says is P or Q or R. So in order to break a disjunction open, we know we've got the rule of disjunctive syllogism, so we'd need the negation of one of the disjuncts. Lo and behold, your loyal instructor has given you that here. So we know that not R will give you, by disjunctive syllogism, P or Q. Okay, so then we're still stuck with P or Q, but lo and behold, we've got the handy not Q, which unlocks the P, and then you're in business. Okay, so let's go ahead and do this proof. Okay, so now you've got the basic strategy of backtracking from the S, seeing what you need here. I need to get it out here. I've got the P. I need to get the P, but in order to get the P, I need to break it out of these two disjunctions. The key to breaking it out is right here. Okay, so let's go ahead and list the premises. We've got P or Q or R, and that's a premise. So remember, I'm justifying my rules, or justifying my lines over here. Line 2, I've got, let's say, not R and not Q, and that's also a premise. Line 3, I've got if P then S, and that's also a premise, and that's what I have to work with in order to build to S over here. Okay, so let's go ahead and do that. So what I'm going to need to do is break not R from 2 by simplification. So I know if I've got on line 2 not R and not Q, then I can conclude not R. Line 5 gives me not Q. I'm going to need that later from line 2 by simplification. I know I'm going to need it later because of the strategy that we did earlier. Line 6 gives me then P or Q. How did I get that? Well, I got that using lines 4 and lines 1, disjunctive syllogism. Line 7, I've got the P or Q, I've got the not Q, I've got therefore P by lines 5 and 6, also disjunctive syllogism. Line 8, I've got S from lines 3 and 7, modus ponens, and S is what I was trying to conclude, so I successfully achieved that. So how did we get it? Well, we got it by at each step, the inference was either a premise, or each line was either a premise, or was derived from a premise according to a rule of inference. Okay, so we then say that this argument here is valid. Okay, and we've proven that directly. Okay, so there's lots more to talk about. I'll do a couple more examples of direct proof. Let's plow ahead.